Please like and subscribe to this channel and press the bell icon to get new video updates.
We're talking about radio on the railroads, but the whole topic of communication and everything that we display in the museum has a connection to railroad communication, including teletype, which we will not be covering, but the many facets of spark transmission, of course, the hollow state tube transmission, and of course, the implementation of transistors in solid state. We're looking at a slide that talks about Thomas Edison. He received a patent in 1891 as a means for transmitting signals electrically. That would be an induction system. He called it the grasshopper telegraphy that allowed the signals to jump a short distance between a running train and telegraph wire parallel to the tracks. So with Mr. Edison's development, we now have communication between railroads, an operating train, and people who are basically on the ground. This is interesting because keep in mind that the main form of transportation back in the late 1800s and the beginning of the 1900s was railroads, not as much aviation. Of course, aviation took off, no pun intended, and a lot of their communication became very sophisticated as well. But the system was successful, but it was not economical. There really was no great interest in communicating between moving trains and the people on the wayside. There was another opportunity here, and this shows Marconi Tower, which commemorates something that happened in November of 1913. And this was actual radio communication with the stations on the way from a couple different destinations from the East Coast all the way to Buffalo. This tower was erected in Binghamton, and Binghamton, which is a wonderful town. This shows that, which is one of the last remnants of that communication that was done using, of course, the telegraphic side of radio at that time. The tower was erected in 1998. It was part of the Marconi Company's effort to communicate with trains communicating with stations as they pass by. There are only a certain number of stations, as you'll see. This tower is nearly 100 feet tall. And again, it dates back to 1913. Other towers, similar, but not exactly the same, were erected in Scranton, Pennsylvania, and Hoboken, New Jersey. On November 25th, 1913, the official first wireless message was transmitted from Scranton to the train traveling to Binghamton, which was moving at 60 miles per hour. The train picked up, the operator at that point picked up 350 words in this historic transmission. Now, this is the station you will see at that time. This is Lackawanna Station. I believe it was the Delaware, Lackawanna, and Western Railroad at the time, just known as the Lackawanna. This is the station that I believe this should be Binghamton. And as you can see, there are two towers with an antenna hanging between them. You can see only one tower here in Scranton, but there are actually two. The photograph only shows the one. It's not a very good photograph. It's quite old. So there was also a station transmitting and receiving in beautiful downtown Scranton. The train we're talking about with this special feature was the Lackawanna Limited. This is their crack train. It left Hoboken at around 10 or so in the morning. I have to move your pictures here. It left Hoboken at 10:15 a.m., would arrive in Buffalo 9 hours and 43 minutes later, around a little before 8 o'clock. Now, you may say, who would go from Hoboken to Buffalo? That's a very good question, and we'll answer that shortly. The Lackawanna Limited is here shown with the antennas that are mounted on the cars themselves, and I'm going to use my pointer. You can see my pointer moving around. They're on the top of the cars, but you really can't see them. because of, again, the detail of the photograph, but they are on there at least 2 or 3 cars, and they're connected with special connectors. This route I spoke of goes from Hoboken to Buffalo. People would generally leave Manhattan by ferry. They would go into Hoboken Station, and the train would take them through New Jersey, through the northeastern corner of Pennsylvania, up into Binghamton, Elmira, Corning, all the way to Buffalo. This was another route people could take, because at the time, the most popular route and a better known route would be the New York Central, which would be going up to Albany, then simply across the Mohawk area till it got to Buffalo. Friedrich Wally was the radio operator on this historic train ride. 30 miles east of Buffalo, Wally, who did not know the call sign for the station in Buffalo, just called radio station. Obviously, at the time, there weren't that many. The operator at the station was maintaining watch that evening because he wanted to communicate with some ship or steamship on Lake Erie. He was located in the evening newspaper building in Buffalo. Thinking he had picked up the steamer, he answered the call, and Wally replied, "This is the Lackawanna Limited." The gentleman thought that he was being scammed, he was being joked upon. It turns out that he said, "Please quit your kidding." And Wally said, "No, I am really on this train." And he then forwarded this information. He thought he was being victimized. That would be the Buffalo newspaper operator, and moved on to be invited to come see the train and the operation, and the outfit that Wally had actually on the train, and the newspaper gladly did so. Here's a train arriving in Buffalo. A lot of people showed up to welcome them. The aerials for the cars were on top of the cars themselves, and you'll see in this photograph you have the rectangular. They're just basically covering the periphery of the cars on the top. They're about, I believe, 18 inches, no more than that, because they had to get under tunnels and bridges. And you'll see that there's the insulators. They're insulators, but they're basically breakaway and disconnectable, so that if they have to disconnect the cars, they won't have any damage to the antennas. In this photograph here, you see the, at that time, radio inspector, 23 years old, David Sarnoff, seated in the wireless room. And he handled the train orders and commercial messages in addition to that, in addition to the Mr. Wally. The antennas are quadrangular. And I mentioned before that they were on top of the cars. This really describes them if you're interested in the details. The cars were 65 feet long. Apparently 4 cars were equipped with these antennas. They were raised about 18 inches, as I mentioned. And between the 4 cars was a plug-in socket to allow for disconnection. Here's the operator in their special location on the train itself. The trains were equipped with wireless, and they were independent. They loved the idea because it was independent of sleet, storms, and all kinds of weather that affected the hard connected telegraph lines. Normally, the process would be the telegraph operator would receive a message at a station or a tower. Then to get the message to the train, they would write it out, put it on a long, it was called a hoop. They held the hoop up. The train, one of the train crew would grab the hoop, remove the message, and throw the hoop to the ground. This is how the traditional telegraph would operate. This eliminated all that. If you look over here, you'll see what is a Wallace style receiver. We'll go into some detail on that. Let's look a little about at the details. The power obtained for the generator storage battery. Of course, the wheels had a generator on them, would charge the batteries. The system used 2 kilowatts of power for the wireless service. The transmitter was a 1 kW Marconi set. Technically a range of 50 miles, but some accounts say 100. There were no reports of dead spots between stations from what I read, but we don't know exactly how true that is. The idea was that as those who go to sea and can send and receive messages, even news, any kind of updates, the installation of these sets on the railroad will allow for the same type of promised service. Now, the receiver is this Wallace system, and it was made by the Paul E. Wallace Company in New York City, at a spherical Audion tuner. The problem would be a few things. There would be the local noise of the moving train, and it was very poor. The antennas were low to the ground, and according to my friend Ed Gable, who analyzed this information, with the fragile filament, this system was destined to fail right from the beginning. It was only that the Navy put an end to it, and we'll see why shortly. Here's that Wallace valve detector. And this is the state of the art at the time. I believe these were manufactured in 1911 and then on, or around that time. Marconi Company had certain expectations, as you would think. They were a very mercenary company. And you know that they had setups on the Titanic basically to make money, to send communications messages for pay. They want to do for railroads what they did for maritime. They want to transmit news to trains, which they did, and people were very excited about that. There were actually news reports sent to the train during this experimental people, and people were just fascinated with the news being sent to the train. They didn't have to stop and buy a newspaper. And at that time, I believe there was at the Mexican-American War, some situation going on. And they were getting updates on that in the train without reading a printed newspaper. 4 days into the experiment, a traveling salesman sent a commercial message, again for pay. The railroad had expectations. They wanted to see if wireless was a reliable form of communication, more reliable than the landline telegraphs they had been using. And of course, what remained to be determined is, will thunderstorms affect the reliability of the system? They wanted to prevent accidents, which is always a major factor on railroads. They wanted to use better communication to prevent the accidents. And to deliver train orders, as I discovered earlier, even having the train having to slow down or stop, which costs money, this type of transmission directly to the train from towers and stations would be very lucrative for a railroad. But it ended. On April 16th, 1914, the noise of the train was confusing and distracting. The range of communication was shorter than we had talked about. Of course, you're going through the Pocono Mountains. You're going through a lot of hilly topography. That caused problems. But it was the Navy who brought a halt to the activity, primarily because the frequency used by the railroad was the same as that used by the Navy and its ships at sea. And the railway transmissions blocked critical Navy communications. So on April 16th, 1914, the whole project was called to an end. The next movement in communication between trains and the ground was Union Switch and Signal Company's invention called train phone. They developed this for the Pennsylvania Railroad. Pennsylvania Railroad is referred to as the standard railroad of the world. It did a lot of very innovative things over the years, more than most people realize, and that they want to communicate between train crews and moving trains, dispatchers, and tower operators. It was first used also by the Kansas City Southern and to a lesser extent, Duluth, Mesabi, and Iron Range. It did not use radio, but electromagnetic induction. It was first installed north of Trenton, New Jersey. Now, this is a 52-mile amount of trackage that the Pennsylvania Railroad had that came out of Trenton, which is part of their main line to New York City. And it went up to a town called Manuka-Chunk. That's in New Jersey, not to be confused with Monk Chunk, AKA Jim Thorpe in Pennsylvania. Manuka Chunk. It was installed in 1942. It was for the transmission of orders and any information connected to train operation. Ironically, it connected with the Lackawanna. There's an interchange there. They basically also wanted the conductor of the train, who usually was in the caboose, to speak to the engineman. There's a connection with the Delaware, Lackawanna, and Western in Manuka Chunk on this Belvedere, Delaware Division branch. And it went through Washington, New Jersey. And again, I said 52 miles, it's a 54-mile route north of Trenton. Carrier currents were used to generate and utilize rails and parallel poles, making it unnecessary to use radio frequency. Messages were confined to radio property. There were satisfactory results. They were so many happy reports that the installation was put into several hundred locomotives, nearly 100 cabin cars, aka cabooses, 6 switching towers between Harrisburg and Pittsburgh. Now, the reason we'll see why it's between Harrisburg and Pittsburgh. It's not just because it was one of the heavy traffic areas. It was designed to reduce delays and keep dispatchers fully informed of train movements. It was allowing for more efficient planning. The system was intended to allow the engine and caboose to communicate. The antenna setup was an inductive signal in the communication lines, which would have been ferrous or copper right along the right way of the train. So it would be like the telegraph lines. Those generally the telegraph communication lines were used as the carriers of the signal. There were rules of thumb set up, procedures, protocols, as you would call them, and these would be as such. You would have, are you communicating with the proper persons? Is the conversation finished? Make sure all that who are involved with the conversation were heard and understood, so that there would be no miscommunications and no misunderstandings. On the right side, you see a artist's conception of this unit with on and on switches and a selection of local and distance communication. Here's a communication with this is a gentleman most likely in a tower or a station, and he's communicating with the train. This was an audio system. This was not the Morse code at this point. This was the transmission of audio. In the engine and cab, you'd see a set like this. This is the control box. There'd be more technology that was involved, but this is the main operating here. Very simple system, on, off, and I believe there were 2 channels. In the caboose, you'd have another similar setup. In this way, the engineman, or you would call it the driver in Europe, would be communicating with the caboose. Train phone signals were inductively coupled in the wayside telephone and signal lines. They would have handrail antennas on locomotives and cabooses, which acted as carriers of the signals. And I'm using the word antenna very freely. The system never worked well, and it was useless in electrified territory. So when I said it was in particular operation on over 1,000 miles between Harrisburg, there's 1,000 miles of trackage between Harrisburg and Pittsburgh. Of course, the distance is not 1,000 miles, but there were other branch lines that use this. But on 1,000 miles of their system, they had this train phone. They could not use it between Harrisburg, Philadelphia, New York, and Washington, because you had your overhead power that ran the electrically powered locomotives. That was then 25 cycles, 11,000 volt AC. That completely interfered with the system, and so it was useless in that electrified territory. Now, here's an example of a locomotive. This is a restored E8 diesel with the antenna on top. That's what it would look like. I do not have a picture of a caboose itself. What I do have is a model caboose showing what the antenna would have looked like on one of their classic was it N5 cabooses that were used by the Pennsylvania Railroad. Here's an overhead view of the same caboose in a simulated rail situation. This is a Pennsylvania Railroad instructional film. This single frame shows how you have the locomotive here, the signal traveling to the wayside pole lines, and the signal will go down the pole lines. Now, we've seen some of these observation cars used on the passenger trains here and in other states, especially in the western states. I've talked to different people. Apparently, this may have been used for train phone, but in many cases, a lot of these antenna arrangements were used for entertainment of the guests in the lounge cars and these observation cars. And generally, they would have an AM set up for people to listen to the radio, which in itself could prove problematic. You're going in and out of different towns, but again, I'm sure there was some value to it. Limited train phone communication between equipped engines, cabins, and trains was being inaugurated in 1949. Train phone was a somewhat successful program, but as you see it also would come to an end. The whole idea, again, was to report maintenance of way situations, emergency situations, safety hazards. When the operators, the train crew is in the caboose, the reason cabooses look the way they do is so they can observe the train from their end. And if for some reason they see smoke coming out of the wheels, and as you know, if you've been following the news, there have been issues with axles and bearings on trains overheating and causing mishaps, derailments. There's a lot of that's been very noticeable recently. But if they see such smoke or what they call a hot box, they can immediately tell the engineer to stop the train, and then they can go down on the ground and inspect it. All train phone equipment was made by Union Switch and Signal. Reception was limited to several hundred feet either side of the dedicated wire. Again, that acted as a stationary antenna. Low frequency system, 3 to 50 megahertz. And of course, you had the antenna with very large dimensions mounted on the trains. They stopped using these on locomotives about 1962, 63. I am very surprised they lasted that long, because at that point, solid state VHF radio gear came along and train phone was quickly scrapped. The Bessemer used this system, but they also had portable phones. And I'm going to show you an example of such a portable phone. It was the size of a lunchbox, a very large lunchbox, and it had a huge antenna coil, at least 3 feet in diameter. Can you imagine a switchman or brakeman carrying this around when they're doing an inspection of the wheel bearings? Look at this. Carry phone was the device that the Pennsylvania Railroad came up with. It was inaugurated in 1946. Same company, Union Switch. It's similar to a walkie-talkie, and it uses could have been used as much as an 88 kilohertz carrier. It used induction and not space radio. PLR announced the development of the carry phone in November of 1946. And this walkie-talkie style unit was absolutely hysterical. It was also used on the same branches, the heavily used Pittsburgh to Harrisburg area, and also the Delaware branch I described earlier. And that, gentlemen, is carry phone. As you can see, it's very convenient, and it's way bigger than a lunchbox. It weighs 29 pounds, and you can have this lovely device following you around all day, hanging from your shoulder. Eventually, you'll develop all kinds of musculoskeletal issues. And this is the carry phone being tested by the Pennsylvania Railroad Ergonomics Lab. Actually, this is a simulation of carry phone between train crews with onboard personnel. That, by the way, that is not is a bit of a cartoon. This is more likely what it could have looked like when they were testing them. But this is the carry phone resting in the cabin car. It had rechargeable batteries. Inconvenient, but at the time, I'm sure it was a great thing to have around. Here's the employee checking the wheel bearings and any safety issues, and would report that either to the cabin car or back to the engine. It does mention on there that the weight of the item is what, 29 pounds. Same picture again, shows you it being charged and shows you the operator using it. Edward has provided this excellent information. I know of no HF system that was successful. Only enormous efforts prior and after World War II, developing the FM on VHF, saved the day using World War II military short-range technology for low noise FM communication. And that really is what saved the day for the railroads. And thank you for Mr. Armstrong. See if you can pick out which one we're talking about, who gave us FM. Erie Lackawanna had radio in the 1950s. If you notice, even models will say radio equipped on their cabooses. And this is true radio, not this carrier current business. The Lehigh Valley never had radio until Conrail took over. And my understanding is when Conrail took over, Lehigh Valley was basically swept under the rug because you already had the Erie Lackawanna, and you had other, and you had the New York Central going to Buffalo, serving all those industrial areas. I want to thank Mr. Springer for that information. He retired from Amtrak. 1950s. Little phone. This was developed by Howard Crafters. This was an FM system. It had multiple batteries in it. It was good for use in cars, but it was also used on the railroad. Here's an example of little phone by Howard Crafters in use. Note that it on the side of it, it says 161.25 megahertz. This is the year of 1955. Thankfully, these excellent units have come along. They're small. They were relatively reliable. If you look at the locomotive carefully, it's the Milwaukee Road. And you might wonder why there. I see a connection because Hal Crafters was in Chicago, and the Milwaukee Road was a main terminus in Chicago. Here's a picture of a little phone. This, by the way, is from our museum collection. It shows you that it was set up for 161.25 megahertz. It showed you the batteries on the inside. I didn't dig into it further to show you more of the circuitry, but this apparently was set up in December 21, 1955, as the initials of who put it on. As we get closer to the 60s and into the 60s, we have the transistorized units. This one is from Motorola. As you can see, this is being marketed for the construction and maybe other types of transit that would have vehicles, but this was also used on railroads. Motorola played a big role in railroad communications. And then there's this. You may have heard of the railroad car, the Magellan, that was used as a communications car, and I believe it dates back to Roosevelt's era. These trains have been renovated multiple times. This one shows the JFK train from about 1971. This was his communications car. And they also had ham station W3 WTE for White House. This is March 1961, the presidential train communications car. It's a history of both official and amateur communication activities. It has that history. Interesting array of antennas. Again, we have those roof-mounted antennas like we saw earlier, but these are a little bit, I think, better in quality and better design. Again, they're kept low to go through tunnels. Radio operators used a wire inside an insulating tube on the top with standoffs about 6 inches above the metal roof of the car. That was later changed to copper tube. For better results, telegraph lines along the tracks provided a lot of clicks, especially in the areas of the southwestern United States. So again, there were some issues with interference. 1970s brings us some other technology. We're now looking at a product in the late 1960s by Motorola called Motran. It was all solid state. It replaced their Motrac system. It had internal power converter to change from 72 volts DC to 12. The standard power in a lot of locomotives was then, again, at least 72 volts DC. That's what they picked out. I don't know the reasoning for it, but that's what they did. A 75 ohm antenna. It was rack mounted, and it had the Association of American Railroads control set. This is an example of Motran. This is the type of system you'd have in either a caboose. You could also have it in the locomotive, but this is the newer technology. Here's an example of a Motran that apparently was selling on eBay, of all things. This is an example of Motran that's pretty well weather beaten. It is from a train, I believe, in the southeastern United States. That's where the photograph came from. And as you can see, there are a couple frequencies, one for the yard and one for when you're traveling on the road. In the early 70s, Motorola came out with Micor. It was a top of the line item. It was superseded by the clean cab design of 1972. We'll talk more about clean cab shortly. Last use was in 2023 when the FCC issued new technical standards. It used standard mobile vehicle components, and it had the 72 volt DC converter in it and a surge suppressor because of the fluctuating current. Here's an example of the Micor control unit. It has a key, it has your antenna out, and it has all your control, a plug for all your control cable. What does clean cab really mean? Let's talk about that. Okay, this is more of a railroad issue, but design is a big part of all communications. First of all, it has an excellent ergonomic design. It has sleek, modern, lines to it. It's easy to reach controls. Layout of the controls is more intelligent, thoughtful control of shapes and form factors. Better control interface with the operator. Comfortable seating. Most importantly, as I've told this story before, no sharp edges, so you don't have to worry about having an injury. This is an old locomotive cab. This is the EMD F7. This is one of the large diesels used for passenger service, very common, and also for freight. And this is for an Alco RS1. As you can see, it's sort of a rough-looking cab, and it may not look rough to some. Maybe some people are used to this, but it looks like it was designed by a committee. The same committee that tried to design a horse and came up with a camel. This is an example of clean cab design. As you know, it looks cleaner. It just has better controls and easier to reach controls. This unit here, this Railcom unit, we're going to look at that a little closer later, but you see where I'm circling it. And of course, they have a professionally made sign to tell you what the locomotive number is. It's 5229. That was, I don't know, they had an artist come in and do that. I'm not sure. Motorola Spectra was part of the clean cab radio design of 1991. Association of American Railroad had a new frequency allocation plan, and it involved a 12.5 narrowband channel arrangement. On those frequencies, you see them, you can read them as well as I can. And it had 7 National Oceanic and Atmospheric Administration weather channels from 100 to 106, so you can even get the weather on the radio. This is the Astro Spectra type unit. These sort of not changed too much, but now that you'll see they've changed a bit with really fancy screens. So you've got analog communication from 147 to 174 megahertz. Westinghouse Air Brake Company, WABCO, developed radios in the 60s. In 1970, they sold radios to the comply with AAR standards. Aerotron made radios under the WABCO licensing and other brand names. You'll see that sub-licensing. Finally, Harris gets on the train. The history. In the mid-1970s, Harris and RF Communications sold their VHF-FM, land mobile two-way radios, and these two particularly, to the railroads for voice communication on 160 megahertz band. They're crystal controlled with a maximum of 12 channels, and you had your crystals for each channel. Transmit and receive. 25 watts, but 50 or 100 watt versions were available. They were also used to transmit data for remote control of slave locomotives on very long trains. The 5 watt VHF portable transceiver was designed for railroad use by installing handheld radio modules in a larger package that can hold bigger batteries to provide longer operating time. Here's an example. This one had multiple batteries in it, and it had, simplified controls, but it was a very sleek design. It had your antenna attached to it. It was pretty convenient to carry. It had a full-size quarter wave antenna, push-to-talk handset. These transceivers could be configured with 1 to 6 crystal-controlled channels. They produced these into the mid and late 1970s. Clean cab radio, it's 1979. There is a specification for such. They had to physically fit into a standard locomotive cab. Now remember, we're looking at more ergonomic designs, more finer lines in the design process. They were authorized to 80 channels, and they had narrowband analog FM voice. Harris Clean Cab Radio of 1979, you had the synthesized, was synthesized to provide access to all channels available. Unlike previous crystal control radios, for separate transmit and receive, you now have that synthesized unit, and that made things much more compact, much more reliable. Harris had designed the Alpha line of synthesized radios in '79 for VHF and UHF use, and they had inside a programmable read-only memory that could hold 128 channels that would fit into AAR's frequency requirements. Here's an example. This is the prototype. And by the way, come to the museum, take a look at this actual radio. It's on display in our Made in Rochester display, which is absolutely gorgeous. I'm going to thank Duncan Brown for his great help in photographing this and telling us about it. This was the first engineering prototype of the Alpha unit. It had a sheet metal chassis. 1983, the Clean Cab radio was resurrected with cast aluminum chassis and given model number Alpha 1500. Before going into production, it was sold to Aerotron in 1985. Aerotron sold it with some changes to Frary in 85 and 93. So it's a Harris design, but these other companies manufactured it for railroad use. This is a side note, if I may. SkyTrain, which is in Canada, British Columbia, is a driverless system. That makes me nervous. But anyway, it's a driverless system, and it uses the Harris Alpha 2000. They're full duplex receivers as a UHF radio link. That I can rely on, but no driver and no engineer. The Union Pacific Railroad, and I particularly want to call out, they have a main dispatch center, one dispatch center. You don't have little towers all over the nation. used to have a tower every several miles. There's some, but generally there aren't that many. And everything is controlled out of one location, and this is in Omaha, Nebraska, referred to as the bunker. It uses radio communication, and there are over 800 towers on the Union Pacific system. Union Pacific feels there are 5 ways to get information in their training. The training video will say personal knowledge of the equipment and the line and the process, the timetable, which is an official record, printed papers, which would be orders and instruction, wayside signaling, and finally the dispatcher. The dispatcher often gives special commands as to what type of train movement or what hazards or what situations are to be encountered. This system now incorporates GPS. The entire system calculates speed based on geographic topography. It takes your GPS information. It looks at the track conditions. It has a lot of this on records. It looks at the track conditions from based on weather, speed restrictions based on activity, and all the other hazards, and comes up with a how you can safely travel. We're looking at a safe stopping distance. Now, Alsaldo, which I understand is an Italian company, has a display on the Alaskan Railroad, motor power. This also has very intelligent systems that communicate with the main communication center and the engine itself as to what speed you are going and perhaps whether you should slow down. And we'll talk about this in a minute. They've come up with what's called the warning curve, meaning this is how much time you have to stop and how fast you should be going, all these factors. Burlington Northern Santa Fe has this display. This is a Wabtec display, and this would be in every locomotive. This includes commuter trains, even though Burlington Northern Santa Fe doesn't have commuter trains. Commuters also have this type of technology. Now, what they're saying here is you need to start braking in 69 seconds. The train crew is getting a warning, and they have 69 seconds to go into braking and stop the train or to slow down. And if they don't, they get this. The master control, in this case for Burlington Northern Santa Fe, is in Fort Worth, Texas. They're going to say, okay, we've taken over your engine. You are no longer in control of the engine. We are setting it into braking mode for you. So someone hundreds and hundreds of miles away, maybe 1,000 miles away, is putting it into braking by remote control. How is this done? This is an example of the antennas atop the roof. Obviously, there'll be satellite communication. There'll be microwave communication. There's communication with the 800 towers. This is all a very tight integrated system. And where is it controlled from? It's controlled by this bunker in Fort Worth, Texas. Burlington Northern Santa Fe's control bunker. This looks like something out of a space movie. I've had someone make a nasty comment to me recently that American railroads need to be improved upon. We're backwards. This doesn't look too backward to me. Trainmaster takes the drudgery out of radio communication, railroad communications. I note this as a sort of a play on words. This locomotive is referred to as the Trainmaster. It was built by the Fairbanks Morse Company. Ironically, I wanted to show this engine, and ironically, what's on top? One of the antennas I talked about earlier, one of those rooftop antennas that the Pennsylvania used for train phone. Of all things, what a coincidence. All right, but Trainmaster is something else. This is a product from General Electric. Their transportation division is very advanced, and this is one of their products, as it says, Railcom. It's a Trainmaster unit, and this is what you may see in most locomotives now. This has a computer screen, it has a touchpad, it has GPS. Let's look at the features. The main features include the GPS for locating the train, a lot of other fancy things, or you could, you could change the menu to various languages. It has day and night display mode, all kinds of nifty things. It has liquid proof keypad, so if it's raining, water gets in there. You spill your coffee, hopefully not spill another drink what you're not supposed to have according to what railroads call Rule G. That means no alcoholic beverages. But say you just spilled coffee or milk, something like that, you don't have to worry about it. It connects with this Moto Turbo, which is another system that Motorola has came up with as a Motorola system. It has a 1,000-channel capability, has ruggedized housing, it has night and day display. We've mentioned that already. Multi-voltage operation. And this is interesting. It has data application interface. It has an Ethernet connector. So in a lot of trains, they do communicate digitally, and you can have remote computers or other digital devices that communicate through the radio to get out into the outside world. And that's using this data interface with the internet connection. Here are all the specs. I could read them to you, or you could check them at a later time. There's a lot of neat things added to this. You can add a public address system if it's used on a passenger train. I'm sure Amtrak has a lot of this in their systems. Commuter trains can also use systems like this. I mentioned, here it is, your passenger train announcements. A lot of nice features. It really is a big part of the clean cab revolution. It's taken decades, but it really has come to pass. Here's a artist's conception of what the screen would look like, your transmit and receive frequencies, and all kinds of other fascinating information, time of day, how good your signal strength is, communicating with the outside world. Moto Turbo is a Motorola digital radio product. It's marketed to business and industry. It has a European compatibility. And as you can see, it has a lot of modern features on it. It has the VHF range between 30 and 300 megahertz, UHF 301 gig. These ranges fall into the DMR equipment spectrum here. It mentions all that. I'm not going to go into that detail, but as you can see, it has really evolved quite a bit. It has your favorite CT/CSS on it, so you can have no interference if you have two signals going on the same channel. And you're familiar with that from your ham work. I want to thank all these lovely people who are kind enough to help me with this presentation. What we're looking at now, especially in light of future events, if I may have an epilogue, you're going to see a lot more data added to the communication system. And I believe that these systems are capable of carrying a lot of data to monitor other, axle issues, wheel issues, etc. So you're going to see a lot more sensors on trains. You're going to see not just outside devices that read the train as the train is passing by, but internal sensors on a lot of trains, especially on maybe hazardous material cars. I mean, I see these things coming down the road. These communications advances, I think, will help us have safer railroading. And it certainly has evolved. It evolved from something very basic over 100 years ago to a very amazing integrated data system of today. So I want to give you my kindest thanks for listening to this tirade of railroad fun.
Please like and subscribe to this channel and press the bell icon to get new video updates.